Hey guys, and welcome back to the channel. Tonight, we're going somewhere truly impossible. A place where the sun has never shone, where the temperature hovers just above freezing, and where the weight of the world is literally pressing down on every single atom of your body. We're not talking about outer space. We're talking about the final frontier right here on Earth. We are diving headfirst into the abyss. Close your eyes for a moment. Just listen to the sound of my voice. Now, imagine yourself sinking slowly through the water column. You feel the warmth of the surface fade. The light begins to dim, turning from a brilliant blue to a faded, ghostly gray. The familiar world of tides and waves disappears entirely. You are now entering the midnight zone, the vast, lightless ocean that begins around 1,000 meters down. If you think the surface of the Earth is well known, consider this. More than 80. We have better maps of Mars than we do of the deepest parts of our planet. This is a journey into the abyssal pelagic and the Hadal pelagic zones, the crushing eternal dark, where life shouldn't exist, but somehow, miraculously, it thrives. This is where the physics of survival are rewritten, and the creatures that call this realm home look less like anything you've ever seen, and more like nightmares sketched by a cosmic hand. If you're anything like me, you find a certain strange comfort in the exploration of the unknown, especially when it's wrapped up in the deep, soothing hum of a documentary soundtrack. If you are ready to venture into the deepest, darkest corners of Earth with me tonight, then please take a moment right now, hit that like button, share this video with someone who needs a good, deep dive into the mysteries of our planet, and of course, subscribe to the channel. And seriously, guys, please activate the bell button for notifications for our new videos. We have so much more planned for you, and you don't want to miss our next exploration. Now, let's talk pressure. When you dive into a swimming pool, you feel a slight pressure change in your ears. Every 10 meters you descend in the ocean, the pressure increases by 1 atmosphere. That doesn't sound like much until you realize that the average depth of the ocean is around 3,700 meters. But we aren't talking about average depths tonight. We are going to the trenches. We are talking about the Hadal pelagic zone, named after Hades, the Greek god of the underworld. This zone starts around 6,000 meters and descends to the deepest point ever measured, the Challenger Deep in the Mariana Trench, nearly 11,000 meters below the surface. At 11 kilometers down, the pressure is staggering. It's over 1,100 atmospheres, or roughly 16,000 pounds per square inch, psi. To put that into perspective, imagine taking the weight of 50 fully loaded jumbo jets and balancing them all on your chest.
That is the force exerted on anything that dares to enter this realm. It is enough pressure to crush standard steel submersibles into mere flakes of metal. How do we even begin to explore such an extreme environment?
For centuries, the deep sea was protected by this insurmountable physical barrier. The first serious attempt to map the deep ocean began with the HMS Challenger expedition in the late 19th century, which used weighted ropes to measure depth. It was a painstaking, slow, and often inaccurate process. Today, the technology required to pierce this veil is just as complex and arguably more challenging to engineer than building rockets capable of reaching the moon. We rely on highly specialized, remotely operated vehicles, ROVs, and autonomous underwater vehicles, AUVs, which are often constructed using incredibly dense titanium alloys and complex ceramic materials designed specifically to withstand piezophilic conditions, that is, environments defined by extreme pressure. Think of the Deep Sea Challenger, the submersible piloted by filmmaker James Cameron in 2012, which successfully descended to the Challenger Deep. That vessel was designed as a vertical torpedo with a pilot sphere barely wide enough for one person, encased in walls of steel 9 centimeters thick. The challenge isn't just surviving the pressure, it's maneuvering, collecting samples, and transmitting data back through kilometers of water, which acts as a massive signal inhibitor. Every mission is a monumental feat of engineering. But the real mystery isn't the engineering, it's the biology. How does life survive here? In the abyssal and Hadal zones, 3 critical resources are completely absent or severely limited: light, warmth, and food. Let's start with light. Beyond 1,000 meters, there is perpetual darkness. This means that the entire ecosystem cannot rely on photosynthesis, the engine that powers virtually all surface life. Instead, these deep-sea ecosystems rely on a sparse, slow rain of organic material falling from above, what scientists call marine snow. This snow is the decaying remnants of creatures that died in the upper layers, and it provides the only external energy source for the scavengers below. To cope with this scarcity, creatures of the abyss have evolved truly astonishing adaptations. Firstly, they are piezophiles, pressure lovers. Their cellular structures, their proteins, and their very DNA are chemically adapted to require these crushing pressures to function correctly. If you were to bring a Hadal Zone creature rapidly to the surface, the drop in pressure would be just as lethal as the increase in pressure is to us. Their bodies would simply dissolve. Secondly, many abyssal fish, like the infamous anglerfish or the vampire squid, are masters of energy conservation. They are often slow-moving, with minimal muscle mass, relying on ambush tactics rather than pursuit. They conserve energy by having slow metabolisms, sometimes moving only millimeters a day, waiting patiently for the next piece of marine snow to drift past, or for an unsuspecting smaller creature to wander into their expansive jaws. And then there is the dazzling, terrifying world of bioluminescence. In the perpetual dark, light is not used for sight, but for communication, camouflage, and hunting. Imagine the anglerfish hanging suspended in the black void. It dangles a modified dorsal fin spine known as an esca, at the tip of which sits a glowing bacteria-filled lure. This bioluminescent beacon acts as a dinner bell in the darkness.
It is the only light source for kilometers, drawing in tiny prey directly to the anglerfish's cavernous mouth, equipped with teeth that fold inward, ensuring no meal ever escapes. Other creatures use bioluminescence for camouflage. The deep-sea shrimp, for example, can emit a flash of light in a phenomenon called counter-illumination.
By matching the faint, residual light filtering down from the surface, if any, they eliminate their own shadow, making them invisible to predators looking up from below. Perhaps the most fascinating adaptation is deep-sea gigantism. In the cold, nutrient-scarce environments of the abyss, some invertebrates grow to enormous sizes.
Think of the giant isopod, a crustacean related to the common pillbug, but the size of a football. Or the colossal squid, which can grow longer than a bus. Scientists believe this gigantism is an evolutionary response to the cold temperatures, which slow down metabolism and prolong lifespan, allowing for continuous growth, combined with the need to store energy between rare feeding opportunities.
The sheer scale of the unknown down here is humbling. Every time a new ROV is sent down into a previously unexplored trench, we find something new. It's not just a handful of species. It is potentially millions of species waiting to be cataloged. Consider the recent expeditions to the Karamatic and New Hebrides trenches in the Pacific. Scientists discovered entirely new species of snailfish, translucent, gelatinous creatures perfectly adapted to the crushing pressures, and unique forms of amphipods, tiny scavengers that exist nowhere else on Earth. This is why we call the deep sea the final frontier.
Unlike space, which requires crossing vast distances, the deep sea is right here. Yet it demands a mastery of physics and biology that we are only just beginning to grasp. The exploration of the abyss is not just about finding strange fish. It's about understanding the fundamental limits of life itself.
If life can thrive under 16,000 psi, fueled only by chemical reactions and the occasional shower of decaying matter, what does that tell us about the potential for life on icy moons like Europa or Enceladus, where similar extreme conditions exist? The deep ocean is Earth's largest, coldest, and most challenging laboratory for astrobiology. But there is a dark side to this exploration, and it's not just the absence of light.
Even the deepest trenches are not immune to human impact. research has shown that plastic microfibers have reached the Challenger Deep. The highest concentrations of man-made pollutants, including PCBs, polychlorinated biphenyls, have been found in the fatty tissues of amphipods living in the Mariana Trench. We have managed to contaminate the deepest, most isolated environments on Earth before we have even fully mapped them. This brings a sense of urgency to our mission tonight. We need to understand these ecosystems before our footprint destroys them. Throughout this documentary, we will be diving into the specifics of these incredible zones. We will explore the hydrothermal vents, volcanic cracks in the ocean floor, where life is fueled not by the sun, but by chemosynthesis, creating oases of warmth and vibrant biological activity in the otherwise desolate deep. We will look at the technology that makes these dives possible, and we will meet the scientists who dedicate their lives to solving the riddles of the Hadal Zone. But before we go any deeper, I want to hear from you guys. We talk a lot about the fear of the unknown. We romanticize space travel, but the deep ocean often triggers a deeper, more primal fear in people: thalassophobia. So, here's my question for the comments below. If you had the choice between being dropped alone in the deepest part of the Mariana Trench in a pressurized suit, or being launched alone into the vacuum of space, which extreme environment terrifies you more, and why? Let me know your thoughts down below. We are about to leave the familiar behind. We are shedding the light, the warmth, and the noise of the surface world. Prepare yourself to enter a silent, crushing world of eternal darkness, where every flicker of light is a living creature, and every moment is a battle against the physics of survival. Welcome, friends, into the abyss. Our journey begins now, as we descend past the continental shelf and into the true deep, past 2,000 meters, where the first signs of the truly strange begin to appear. Past 2,000 meters, where the first signs of the truly strange begin to appear. And just like that, friends, we have entered the bathypelagic zone. Forget everything you know about light. We are now in the midnight zone. Below 2,000 meters, the sun has officially given up. Not a single photon of sunlight penetrates this depth. It is a world of absolute, crushing, eternal blackness. Look around you. You won't see anything unless it wants you to see it. And when it does, it's not the sun illuminating the scene. It's the creature itself. We are now in the kingdom of bioluminescence. If you see light down here, it means one of three things: dinner, a date, or danger. The pressure. Oh, the pressure. At 2,000 meters, we are dealing with over 200 standard atmospheres. Think about that for a second. That is the equivalent of having a fully loaded jumbo jet balanced precariously on your thumbnail. If you brought a sealed plastic cup down here, it wouldn't just crush. It would implode into a tiny, dense disk of molecules. Yet life thrives. How? These creatures are biological masterpieces of engineering. They don't have air pockets or gas-filled organs like the fish closer to the surface. Their bodies are mostly water and specialized proteins that resist compression. They are squishy, gelatinous, and perfectly adapted to distribute that immense force evenly across their structure. They are the pressure. As we sink deeper, passing 2,500 meters, the hunters get weirder. This is the realm of the classic deep-sea monster, the one you see in nightmares, the anglerfish. But forget the cuddly cartoon version. The female anglerfish is pure biological weaponry. Her body is blacker than black, a perfect stealth cloak. And she carries that iconic lure, the esca, dangling from her dorsal fin. This esca isn't just a glow stick, folks. It's a living bacterial culture, glowing with cold blue-green light. It's a beacon in the blackness, advertising a false sense of safety. And the second some poor, unsuspecting lanternfish or hatchetfish swims up to investigate that flicker of hope, bam! That massive mouth, lined with teeth that look like broken shards of glass angled inward, snaps shut. And talk about commitment issues. Did you know about the male anglerfish? He is tiny, pathetic, and fundamentally useless, except for one thing. He finds a female, bites onto her, and then fuses with her. His circulatory system merges with hers. He literally becomes a parasitic sperm bank, a tiny bump on her side, providing gametes when needed. That's a level of dedication I don't think I could manage. Let me know in the comments, what's the craziest biological attachment you've ever heard of? Now let's keep moving. If you're loving this descent into the true unknown, please take a second. Science content, just like this. We are dropping past the 3,000-meter mark now, and the temperature is plummeting. We are talking near freezing, maybe 2 to 4 degrees Celsius, 35 to 39 degrees Fahrenheit. This combination of cold, darkness, and pressure requires extreme efficiency. Energy is the most precious resource down here. Food is scarce, and the cost of moving is high. That's why many creatures here are masters of the ambush. Look at the viperfish, another iconic resident of the bathypelagic. Its teeth are so long they can't even close its mouth. They curve back toward its eyes, essentially locking its jaw open. Why? Because when you finally get a meal, you absolutely cannot risk letting it go. If it's a big meal, the viperfish can unhinge its jaw and swallow prey larger than itself. They are the ultimate embodiment of go big or home when it comes to eating. But wait, we are about to hit the ocean floor, the vast rolling plains known as the abyssal zone. We're crossing 4,000 meters. This is the largest habitat on Earth, covering more than half of the planet's surface. It's flat, muddy, and seemingly desolate. But trust me, it's teeming with quiet life. What sustains this life? If there's no sun, where does the energy come from? The answer is something scientists call marine snow. Imagine standing here, 4 kilometers down, and looking up. You would see a slow, constant rain. This snow isn't ice, it's the detritus of the upper ocean, dead plankton, fecal pellets, shed scales, and the remains of surface creatures. It's a continuous, gentle shower of organic matter drifting down from the sunlit zones above. This marine snow is the deep ocean's primary food source, the lifeblood of the abyssal plain. It's why the creatures here are often called deposit feeders. They literally graze on the seafloor mud, filtering out the nutritious bits that have settled. Meet the sea cucumber, or holothurian. Down here, they are not small, spiky things. They are massive, sometimes translucent vacuum cleaners, crawling slowly across the sediment. They ingest the mud, process the organic material, and expel clean sediment. They are essential for recycling nutrients in the deep ocean, effectively cleaning the planet's largest ecosystem. And look at this bizarre fish, the tripod fish. It sits perfectly still on its incredibly long, stilt-like fins, 2 pelvic fins and 1 caudal fin, elevating its body above the soft sediment. Why? To conserve energy and to position itself perfectly to catch any passing marine snow or small crustaceans that drift by. It's a biological satellite dish, waiting patiently for a signal, or in this case, dinner. Survival in the abyssal zone is a game of patience and low metabolism. Movement is minimized and efficiency is maximized. Many fish have soft skeletons and low muscle density because building dense tissue is too energetically costly and unnecessary in a low-gravity environment where swimming is rare. If you haven't already, make sure you hit that notification bell, because what we are about to explore next is the most alien ecosystem on Earth, and you absolutely don't want to miss it. We are talking about places where the laws of biology are completely rewritten. This water, now pressurized and scalding hot, we're talking temperatures up to 400 degrees Celsius, 750 degrees Fahrenheit, leaches minerals and chemicals like sulfur, iron, and copper from the rock. When this superheated, mineral-rich fluid
bursts back out into the freezing cold deep ocean. It looks like a black chimney spewing smoke. These are the black smokers. The moment the hot fluid hits the cold water, the minerals precipitate out instantly, forming the chimney structure itself, sometimes growing several stories high. This is where the sun dies, and a new sun is born, a chemical sun. For centuries, scientists believed all life on Earth was fundamentally dependent on photosynthesis, the sun's energy. But the ecosystems around hydrothermal vents proved them wrong. This life relies on chemosynthesis. Instead of using sunlight to turn carbon dioxide and water into energy, specialized bacteria use the chemical energy stored in hydrogen sulfide, a toxic, rotten egg-smelling compound pouring out of the vents, to create organic matter. These bacteria form the base of an entirely new food web, a thriving, dense community that exists completely independent of the surface world. It is the ultimate proof that life can exist anywhere, provided there is a chemical energy source. This discovery fundamentally changed the search for extraterrestrial life, pointing us toward icy moons like Europa and Enceladus, which might have subsurface oceans heated by tidal forces. The life forms here are absolutely incredible. First, the giant tube worms, Riftia pachytipola. These things are astonishing. They can grow up to 2 meters, 6.5 feet long, encased in white, chitinous tubes, with brilliant red plumes sticking out the top. But here's the kicker. They have no mouth, no gut, and no anus. They don't eat in the traditional sense. Their entire survival relies on a symbiotic relationship with those chemosynthetic bacteria. The red plume acts like a gill, soaking up the hydrogen sulfide and oxygen from the vent water. This is then transported to a specialized organ called the trophosome, which is packed solid with billions of bacteria. The bacteria do the heavy lifting, turning the toxic chemicals into food, and the worm simply lives off the excess energy. It's a perfect, self-contained biological factory, fueled by geological processes.
Think about that. A creature that doesn't need to eat. What would you do if you never had to worry about grocery shopping again?
Tell me in the comments. Then we have the Pompeii worm, Alvanella pompeiana. This worm is officially the most heat-tolerant complex animal on Earth. It lives right on the chimney walls, with its tail end bathed in water up to 80 degrees Celsius, 176 degrees Fahrenheit, while its head, covered in a fleece of bacteria, sticks out into the cooler water. This is biological madness. Most life dies above 50 degrees Celsius because proteins start to denature, but the Pompeii worm has somehow adapted to withstand these insane thermal gradients. The vent ecosystems are not stable, though. They are ephemeral. Vents can be active for decades, creating a thriving oasis, and then
they can suddenly shut down as the tectonic plate shifts or the magma source cools. When that happens, the entire ecosystem dies out. So how does life spread? Scientists believe that the larvae of these vent creatures, tube worms, crabs, limpets, must float in the open ocean, waiting, sometimes for years, until they detect the faint chemical signature of a new vent forming hundreds or even thousands of kilometers away.
It's a biological lottery ticket, a desperate gamble for survival across the crushing emptiness of the abyssal plain. We're sitting here now, roughly 4,500 meters down, gazing at a landscape that looks like a rusty, bubbling alien city. It's a reminder that life is tenacious, resourceful, and capable of conquering any environment, no matter how hostile.
But the deep doesn't just hold tiny worms and strange fish. It holds giants. As we move away from the intense heat of the vents and back toward the cold, quiet mud, we encounter the phenomenon of deep-sea gigantism. This is a paradox. While many abyssal creatures are small and efficient, others are enormous compared to their shallow water relatives. Take the giant isopod, Bathynomus giganteus. Imagine a woodlouse or a pillbug, but scaled up to the size of a small dog. These armored crustaceans can be over 70 centimeters long. They are the scavengers of the deep, lumbering around the seafloor, ready to feast on any large carcass, like a dead whale or shark that might have sunk down from the surface, a phenomenon we call a whale fall. Why gigantism? There are a few theories. One is related to cold temperatures, which slow metabolism and allow for longer lifespans and continuous growth. Another theory is related to pressure itself, which may affect cell size. But perhaps the most compelling reason is food scarcity. When a meal is rare, being big allows you to store more energy, survive longer fasts, and outcompete rivals when a feast finally arrives. And speaking of giants, we can't talk about the deep ocean without mentioning the undisputed king of invertebrate size, the colossal squid, Mesonocothothus hamiltonii. While the giant squid is impressive, the colossal squid is heavier, potentially reaching 14 meters, 46 feet, and weighing up to 750 kilograms, 1,650 pounds. Its eyes are the largest in the animal kingdom, bigger than a dinner plate. We rarely see them, but we know they exist because their primary predator, the sperm whale, brings back the scars. Scars from massive rotating hooks embedded in the colossal squid's tentacles, suggesting battles of epic proportions in these crushing depths. Imagine two behemoths fighting in the pitch black, illuminated only by sporadic bursts of bioluminescence. If you haven't shared this video with a friend yet, please do. Let's get more people to witness these unseen worlds. Now, let's address the ultimate limit of life, the Hadal Zone. We are currently skirting the edges of the abyssal plain, But the Earth is not flat down here.
It is wrinkled by immense chasms, the ocean trenches. These trenches are scars where one tectonic plate is sliding beneath another, creating the deepest points on the planet. We are talking about depths past 6,000 meters, down to nearly 11,000 meters, 36,000 feet, in the Challenger Deep, the deepest known point in the Mariana Trench.
This is the Hadal Zone, named after Hades, the Greek god of the underworld. It is a place of unbelievable extremes. At 11,000 meters, the pressure is over 1,000 times that at the surface.
That's like having 50 jumbo jets stacked on your thumbnail. It's a pressure so intense that it actually changes the chemistry of water, increasing its density and lowering its freezing point. For decades, scientists debated whether anything could survive down there. The general consensus was that the pressure would destroy the complex chemical bonds necessary for life. But guess what? Life finds a way. The key to surviving this ridiculous pressure is a compound called TMAO, trimethylamine N-oxide. Shallow water fish use TMAO to stabilize their proteins. But Hadal Zone organisms, like the Hadal snailfish, have evolved to produce TMAO in massive quantities. It acts like an internal scaffolding, counteracting the compressive forces and preventing the pressure from crushing their proteins and enzymes.
However, there is a limit. Studies suggest that the maximum depth at which complex vertebrate life, fish, can survive is around 8,200 meters. Beyond that, the TMAO required to maintain protein stability becomes so concentrated that it interferes with basic cell function. The fish essentially poison themselves trying to stay uncrushed. But just because fish hit a limit doesn't mean life stops. In the deepest parts of the trenches, past 9,000 meters, we find amphipods, small shrimp-like scavengers, and bacteria. These organisms are the ultimate extremophiles. They are living under conditions that would instantly vaporize human bone structure, yet they are thriving, munching on whatever organic material manages to sink to the very bottom of the world. Think about the timescale involved. Anything that sinks to the Challenger Deep has been traveling for months or years. It's the final resting place for countless billions of organisms. The Hadal trenches are essentially the ultimate, high-pressure, incredibly cold garbage dumps of the planet. And what about life down there that we don't know about? Every single time a new submersible, like the Deep-Sea Challenger or the Triton, ventures into these unexplored pits, they bring back something new, something that defies our assumptions. We have explored less than 5% of the deep ocean, and the trenches represent the final frontier of the final frontier. It makes you wonder, doesn't it? What kind of biological secrets are locked away in the sediment of the Challenger Deep? Could there be organisms that rely on processes even stranger than chemosynthesis? Could there be creatures that have found a way to completely bypass the TMAO limit? The truth is, we know more about the surface of Mars than we know about the mountains and valleys in the abyssal and Hadal zones. The deep ocean is the greatest repository of biodiversity and scientific mystery left on Earth.
This entire journey, from the fading light of the continental shelf down into the crushing chemical heart of the deep, underscores one undeniable fact. Life is infinitely adaptable. It does not need sunlight. It does not need warmth. And it certainly does not care about pressure. It just needs energy and water. And it will find a way to thrive, turning the most hostile environments into bustling, bizarre ecosystems.
We've covered the midnight zone, the abyssal plains, the thermal oases of the vents, and the beginnings of the Hadal realm. But there is so much more to uncover. We haven't even touched on the truly colossal geological structures that shape the deep, like the mid-ocean ridges, which stretch for 65,000 kilometers around the globe, the largest mountain range on Earth, entirely submerged and constantly bubbling with volcanic activity. And what about the deep biosphere? Not just the water and the sediment, but the life inside the rocks. Scientists are now discovering vast populations of microbes living deep within the oceanic crust, miles below the seafloor, heated by Earth's core. These are organisms that have been isolated from the surface world for millions of years, living in a slow-motion geological time capsule. We are talking about discovering a massive, hidden ecosystem that might rival the biomass of all life on the surface combined. This is where the abyss truly becomes mind-bendingly huge. And if you want to continue this descent with me and explore the microbial world inside the crust, make sure you are subscribed. Drop a comment telling me, if you could pilot a submersible to any location on Earth, where would you go? The hottest vent or the deepest trench? Let me know. We're just getting started, friends. Friends, we are not just talking about deep ocean trenches anymore. We are talking about interterrestrial life. We are talking about a biosphere so vast, so isolated, that it might as well be on another planet. We left off staring down the geological rabbit hole, realizing that the life we see swimming above the seafloor is just the tip of the iceberg, or should I say, the tip of the tectonic plate. The deep biosphere. That's the scientific term for this incredible, hidden world that exists miles beneath our feet, inside the crust itself. And listen up, because this is where the numbers get absolutely staggering. Scientists, primarily through the incredible work of the Deep Carbon Observatory, or DCO, estimate that the biomass of this subsurface life, mostly bacteria, archaea, and tiny eukaryotes, could be 15 to 23 billion tons of carbon. Guys, that is hundreds of times the carbon mass of all the humans on Earth combined. It potentially rivals the total carbon mass of all surface life, plants, animals, fungi,
everything.
Imagine that for a second. We spend all our time looking at the vibrant jungles, the vast forests, the teeming surface oceans. And we miss the fact that Earth's largest ecosystem is cold, dark, and crushed under imaginable pressure. But how does it survive? Forget photosynthesis. There is no sun down there. These organisms are the ultimate chemosynthesizers. They are masters of consuming the very rock they live in. They eat hydrogen, methane, sulfur compounds, and iron, all generated by geological processes' internal engine, not the star above us.
Think about the conditions. We are talking about temperatures that can exceed 120 degrees Celsius, 250 degrees Fahrenheit, pressures that would instantly crush a modern submarine, and a food supply that is so scarce it makes the surface ocean look like a buffet. These microbes, these kings and queens of the deep, are the ultimate survivors. We call many of them piezophiles, literally pressure lovers. They don't just tolerate the crushing weight of the overlying rock and water, they require it to function. Their cellular membranes and enzymes are specifically tuned to that high-pressure environment.
If you brought them up to the surface, they'd explode. Or at least, their internal machinery would completely seize up. And then you have the thermophiles, or hyperthermophiles, thriving in the boiling hot zones near magma intrusions, or deep hydrothermal systems. It's a hot, crushed, dark party down there, and they are the only ones invited.
Now here's the kicker that absolutely blew my mind when I learned it. Because food is so incredibly scarce, some of these organisms are living in what scientists call an oligotrophic state. They are starving, but they are surviving.
Their metabolic rates are so low that they might only reproduce once every few thousand years. Seriously, we're talking about life that is essentially in suspended animation, moving at a geological pace.
They are the definition of slow burn. Some scientists have even dubbed them zombie microbes because they are technically alive, but barely metabolizing. They are just waiting, existing for millennia, powered by the slowest chemical reactions imaginable. I want you guys to think about that in the comments. Imagine having a lifespan where you only reproduce once every 5,000 years. What do you think that existence would be like? Let me know your thoughts. And while you're thinking, if you are finding this journey into the Earth's core fascinating, do me a huge favor and smash that like button right now. It really helps the channel tell YouTube that you want more of this deep, dark content. Let's talk about the logistics of finding this stuff. It's not like we can just send down a tiny ROV to peek around. We have to drill. Deep, very deep. We're talking about scientific drilling projects that push the limits of engineering. Ships like the Japanese vessel Chikyu are essentially floating drilling platforms designed to penetrate miles into the seafloor and retrieve pristine core samples from the mantle and crust. The challenge here is monumental: contamination.
When you drill through miles of water and sediment, you are dragging surface microbes down with your equipment. So, scientists have developed incredibly rigorous, almost sterile, protocols to ensure that when they pull up that core sample from 3 miles down, the life they find truly originated there, sealed in the rock matrix for millions of years, and isn't just a surface hitchhiker. They use special tracers and dyes, and they are meticulous about the internal structure of the drill bit itself. It's like forensic science, but for geology.
What these drilling missions have confirmed is that the deep biosphere isn't just a few scattered microbes. It's a vast, interconnected network. We are finding communities of microbes thriving in oceanic crust, in continental shales, and even in deep buried aquifers that have been isolated from the surface for geological epochs. Some of the water these microbes live in is millions of years old, fossil water, trapped since the time of the dinosaurs.
And this discovery has profound implications for our understanding of planetary chemistry. These deep microbes are not just passive residents, they are active agents in geological cycles. They influence the flow of carbon and nitrogen. They play a role in the formation of mineral deposits, and they might even be generating some of the methane that leaks up from the seafloor.
We used to think these cycles were purely physical and chemical. Now we know they are fundamentally biological. Life is literally shaping the rock cycle of our planet. This brings us to one of the biggest mysteries in science, the origin of life. For decades, the standard model was the primordial soup, life starting in shallow, sunlit waters. But the discovery of these robust, rock-eating ecosystems deep underground has provided a powerful alternative theory. What if life didn't start on the surface? What if it started deep inside the crust, protected from the brutal early Earth conditions, the massive asteroid impacts, the intense UV radiation, the volatile atmosphere? Down in the rock, near hydrothermal activity, all the necessary ingredients are present: heat, water, chemical energy, like hydrogen and methane, and protection.
One of the most exciting locations that bridges the gap between surface vents and the deep biosphere is the Lost City hydrothermal field in the mid-Atlantic. Unlike the black smoker vents we talked about earlier, which are sulfur-based and super hot, Lost City vents are white, towering structures made of calcium carbonate, and they operate at lower temperatures, driven by a process called serpentinization. Serpentinization is magic, geologically speaking. It's a chemical reaction where seawater reacts with mantle rock, specifically olivine, and produces massive amounts of hydrogen and methane, perfect food sources for chemosynthetic life. It creates alkaline fluids that are rich in the energy required to stitch together organic molecules. Many scientists now believe that these types of low-temperature alkaline systems, whether on the seafloor or deep inside the crust, provide the most plausible cradle for the very first living cells on Earth.
If you are just tuning in,
and your mind hasn't been completely blown yet by the idea that the Earth is essentially a massive living sponge, make sure you hit that notification bell so you don't miss the next stage of our descent. Now, let's pivot slightly and return to the Hadal Zone, the trenches, because the deepest ocean floor is often the gateway to the deep biosphere beneath it. We've talked about the crushing pressure, but the life forms that inhabit the Hadal Zone, the deepest trenches below 6,000 meters, have evolved specific, bizarre adaptations that show how pressure shapes biology.
Take the Hadal snailfish, often cited as the deepest dwelling fish known to man. These guys are incredible. They live down in the Mariana Trench, sometimes past 8,000 meters. They look almost fragile, gelatinous, and translucent. Why? Because they have minimized the use of rigid structures, especially bone. If you were a surface fish, your bones would be necessary structure. Down there, those bones become a liability. The pressure forces water out of cells and interferes with protein function.
The snailfish and other Hadal inhabitants have evolved specific molecular strategies to counteract this. They use organic molecules called piezolites, like trimethylamine N oxide, or TMAO, that stabilize their proteins under extreme pressure. TMAO essentially wraps around the proteins, acting like a molecular shield, preventing the pressure from denaturing them.
It's an internal pressure suit built right into their chemistry. But here is the limit, and this is fascinating. Scientists believe that around 8,400 meters, the amount of TMAO required to maintain protein stability becomes so high that it actually starts to interfere with basic cellular functions. It becomes metabolically too expensive, or chemically too disruptive, to hold any more of the stabilizer.
This is why we rarely, if ever, find fish deeper than about 8,400 meters. That depth is thought to be the physiological limit for vertebrate life on Earth. Below that, the pressure belongs entirely to the invertebrates, the amphipods, the copepods, and of course, the ever-present, tireless microbes of the deep biosphere.
We've explored the physical limits of life in the trenches, and now we understand the chemical limits of life inside the rock. But what does this mean for the rest of the universe? This is where the abyss truly becomes the launchpad for astrobiology.
The moment we proved that life could thrive independently of the sun, fueled only by rock, water, and heat, we fundamentally redefined the habitable zone of the cosmos. Suddenly, the search for extraterrestrial life expanded exponentially. Consider the icy moons of the outer solar system, Jupiter's Europa and Saturn's Enceladus.
These moons are far too distant from the sun for liquid water to exist on the surface, but both are geologically active, experiencing tidal forces from their massive parent planets that generate internal heat. This heat keeps vast subsurface oceans liquid beneath thick, icy shells. And if we have a subsurface ocean, and we have geological activity, which we know they do, based on plumes of water erupting from Enceladus, then we have the exact recipe for the deep biosphere we just discussed. If Europa's rocky core is reacting with its ocean water via serpentinization, that process is generating hydrogen and methane. That means Europa could be teeming with its own version of zombie microbes, living in the dark, hot interface between the core and the liquid ocean, completely oblivious to Jupiter's radiation or the distant, weak sunlight.
The life we are discussing here, the chemosynthetic, slow-moving, pressure-loving, rock-eating life, might actually be the most common form of life in the entire universe. Think about that. We are obsessed with finding intelligent life, or even complex surface life like plants or animals. But statistically, the vast, vast majority of biomass across the cosmos might be these simple, resilient, subterranean or suboceanic organisms. This realization is driving the next generation of space exploration. Missions are being planned right now, like the Europa Clipper, not just to look for water, but to actively search for the chemical signatures that indicate geological energy and the potential for chemosynthesis.
We are looking for the telltale signs of a deep biosphere on another world, based on the incredible discoveries we are making right here in Earth's abyss. I want you guys to weigh in on this. Do you think we will find deep microbial life on Europa or Enceladus before we find anything complex? Drop your predictions in the comments below. I read every single one of them. And seriously, if you've made it this far, you are an absolute champion of the deep. Share this video with someone who loves space or geology, because this connection between Earth's depths and the cosmos is one of the coolest things we've covered. Let's pull back from space for a moment and look at another incredible, almost mystical aspect of the deep biosphere, the way these organisms survive on virtually nothing. We talked about oligotrophs, but let's get into the specifics of how they manage their energy budget. Imagine you have a single grain of rice, and you have to make that last for 100 years. That's essentially what these microbes are doing. They have evolved to be incredibly efficient at energy storage and utilization. Their cells are often tiny, minimizing the surface area required for maintenance. Their DNA repair mechanisms might be slowed down, and their movement, if they move at all, is minimal. In some of the deepest sediment cores retrieved by the DCO, scientists found microbes that had been dormant for over 100 million years, literally since the Cretaceous period. When researchers gave them a tiny nutrient boost in the lab, these ancient cells woke up. They started metabolizing and reproducing, proving that life can persist in a near-zero energy state for periods that dwarf the entire history of humanity. This is not just survival. This is biological immortality, or at least biological persistence on a geological timescale. This raises profound questions
about what alive even means. If an organism is metabolizing so slowly that it only divides once every few thousand years, is it truly living in the way we understand it? Or is it simply a complex chemical structure maintaining equilibrium against decay?
Whatever the philosophical answer, the biological answer is clear. The deep biosphere is a library of ancient, persistent life forms that have mastered the art of geological patience, and the sheer diversity is mind-boggling. When we look at the tree of life, the vast majority of branches, the genetic diversity, belong to the bacteria and archaea, and a huge chunk of that diversity is found exclusively in the deep biosphere. We have barely scratched the surface in cataloging these species. Every time a new core sample is retrieved from a unique geological setting, say a deep fracture zone in the Pacific Plate, or an ancient salt dome in the Gulf of Mexico, we find new phyla, entirely new groups of life that have never been seen before, genetically distinct from anything on the surface. We are talking about discovering entire kingdoms of life right here on Earth, hidden in plain sight, miles beneath us. One of the most extreme, yet vital habitats for this subsurface life is within the deep-sea methane hydrates. Methane hydrates are essentially frozen cages of water molecules trapping methane gas, forming ice-like structures that are stable only under high pressure and low temperature, like on the continental slopes. These hydrates hold absolutely massive amounts of carbon, potentially more than all known natural gas reserves combined.
And guess what? Microbes live there too. Specifically, specialized archaea and bacteria work together in symbiotic communities to consume this methane, preventing much of it from bubbling up into the ocean and the atmosphere.
This process, called anaerobic oxidation of methane, AOM, is one of the planet's most critical natural climate regulators. If the deep ocean warms even slightly, these methane hydrates destabilize, potentially releasing colossal amounts of potent greenhouse gas. But the microbes are the last line of defense, tirelessly eating the escaping methane.
They are the unsung heroes of climate stability, living in a frozen, high-pressure environment that is literally on the verge of melting. This interplay between geology, chemistry, and biology is what makes the abyss so compelling. It's not just a collection of weird animals. It's the fundamental operating system of the planet.
Let's talk about another incredible geological phenomenon that sustains the deep biosphere: deep crustal fluids. As tectonic plates grind and shift, water is often squeezed deep into the crust, sometimes interacting with magma. This superheated, chemically reactive water then circulates through massive fault lines and fractures, creating subterranean rivers of chemical energy. Scientists drilling into the deep South African gold mines, which are essentially boreholes miles deep into the continental crust, have found completely isolated communities of bacteria living in these fluids. One famous example, Candidatus desulphurudus audax viator, was found living 2.8 kilometers deep in a fluid pocket isolated for millions of years. This organism is an absolute marvel. It can sustain its entire life cycle by using only the energy derived from the radioactive decay of uranium and other elements in the surrounding rock. It literally eats nuclear energy. This is life that is completely independent of the sun, completely independent of the surface, and completely self-sustaining based on geothermal and radiolytic energy.
It's a closed-loop system, a tiny, perfect, isolated world, living off the slow, steady decay of the Earth itself. When you look at Disulfurudus, you are looking at the ultimate proof that life is tenacious, adaptable, and almost impossible to eradicate once it takes hold. If you want to know what life on Mars might be like, or how a colony might survive deep underground after a global catastrophe, this is your blueprint.
We are uncovering not just new species, but entirely new modes of existence. And if you are loving this dive into the truly extreme edges of life, please take 1 second, look down, and make sure you are subscribed. We are going to be following up this deep biosphere exploration with a video focused entirely on the search for these intraterrestrial life forms on other planets. So you don't want to miss that.
Now, back to the trenches, because the Hadal Zone also holds secrets about the subsurface. The deepest parts of the trenches are often filled with thick layers of sediment. Sediment that has accumulated over millions of years, trapping organic material that sinks from the surface. This sediment layer is incredibly important because it acts as a massive food source for the microbes living beneath it and the invertebrates that burrow within it.
The Hadal trenches are essentially the planet's deepest trash cans, but that trash is gold for the microbial communities. The sheer volume of organic matter sinking into the Hadal Zone is why we find huge concentrations of life there, despite the crushing pressure. The abyssal plains are often sparsely populated, but the trenches are teeming with amphipods and other scavengers, all feeding on the steady rain of detritus.
It's an inverted ecosystem. The deeper you go in the trenches, the richer the food supply often becomes, creating pockets of dense biodiversity even at 10,000 meters. This concentration of food also means intense microbial activity, leading to rapid consumption of oxygen in the sediment layers. In the deepest parts of the Mariana Trench, for example, the sediment is often completely anoxic, lacking oxygen, just a few centimeters below the surface. This forces the resident microbes to switch to alternative forms of respiration, using things like sulfate or nitrate instead of oxygen. This shift in chemistry is another key indicator that we are transitioning from the surface world's chemistry to the deep world's chemistry. The study of these deep anoxic sediments is crucial because it gives us a window into ancient Earth.
Before oxygen became abundant in the atmosphere about 2.4 billion years ago, the Great Oxidation Event, the entire planet was dominated by anaerobic microbial life. When we sample the anoxic sediments of the Mariana Trench, we are essentially stepping back in time, studying modern organisms that still thrive in conditions reminiscent of the Archean eon.
It's truly a time capsule, preserved by pressure and isolation, and the instruments required to study this are works of art. We're talking about massive, titanium-hulled landers, often called benthopelagic landers, that free fall for hours to reach the bottom.
They are equipped with highly sensitive sensors, specialized pressure-proof cameras, and coring devices designed to take samples without disturbing the fragile chemical gradients of the sediment. They sit on the bottom for days or weeks, collecting data and samples, before dropping ballast weights and floating back up to the surface, where they are recovered by research vessels. The data they bring back is priceless, often revealing creatures that are completely new to science, like the Hadal amphipods, which are often blind and possess remarkable adaptations for scavenging, including incredibly sensitive chemoreceptors to smell food miles away.
They are the vultures of the deep, cleaning up the biggest, most isolated environment on Earth. So, friends, we have traveled from the surface, down through the water column, into the deepest trenches, and now miles into the solid rock of the crust. We have encountered life fueled by light, life fueled by sulfur, life fueled by methane, and even life fueled by nuclear decay.
The abyss is not just a void. It is the largest, most diverse, and most persistent habitat on our planet. It is the engine room of Earth's biology and chemistry, and it holds the keys to understanding both the origin of life here and the potential for life elsewhere in the cosmos. We have only just begun to scratch the surface of this truly massive topic. Next time, we are going to pivot hard into the astrobiology implications of the deep biosphere and ask, what happens when we finally drill into the ice of Europa? What are we realistically going to find? But before we wrap up this massive segment, I want to hear from you one last time. Out of all the extreme life forms we've discussed, the snailfish, the slow-motion zombie microbes, or the nuclear-eating bacteria, which one do you think is the most alien? Let me know in the comments. And if you haven't yet, hit that subscribe button and ring the notification bell so you don't miss a next epic descent. We are still descending, friends.
The journey continues. We are absolutely still descending. And thank you all for dropping those incredible comments about the most alien life forms.
The consensus seems to be split right down the middle between the nuclear-powered bugs and those agonizingly slow, deep-sea zombie microbes. It just proves that the abyss holds a mirror up to our imagination, and what we find down there is often stranger than any sci-fi flick. Now, as we continue our psychological descent, let's leave the vast, cold, slow-motion plains of the abyssal zone for a moment and journey toward the hot spots. We're talking about regions of unimaginable geological violence, where the crust of the Earth is literally tearing itself apart, spewing forth superheated chemical cocktails. We are diving into the world of the hydrothermal vents. Imagine this. You've been cruising through water that is just a few degrees above freezing, pitch black and utterly still. Then, suddenly, the temperature gauge spikes. The submersible lights hit these towering, jagged structures, these geological chimneys that look like something sculpted by HP.
Lovecraft himself. These are the black smokers, and they are the ultimate oases of the deep. These vents form where tectonic plates diverge, allowing seawater to seep down into cracks in the crust.
That water gets superheated by the magma below. We're talking temperatures exceeding 400 degrees Celsius, or 750 degrees Fahrenheit. Now, you might be thinking, wait, how is the water not boiling? The pressure, my friends. The immense pressure at these depths keeps the water in a supercritical fluid state, loaded with dissolved minerals like sulfur, iron, copper, and zinc. When this superheated, toxic fluid blasts back out, meeting the near-freezing ocean water, those minerals instantly precipitate, creating that thick, black plume, hence the name, black smokers. And here is the mind-blowing part. Surrounding these toxic, searing hot chimneys, you find dense, vibrant ecosystems. Forget the sparse life of the abyssal plain. This is a jungle, a deep-sea cauldron teeming with life that has absolutely zero connection to the sun. This is the famous world of chemosynthesis. Instead of relying on photosynthesis, sunlight, to convert carbon dioxide into sugars, these primary producers, specialized archaea and bacteria, use the highly toxic chemicals pouring out of the vents, particularly hydrogen sulfide, the stuff that smells like rotten eggs, as their energy source. They are literally eating sulfur and heavy metals and converting it into biomass. And what eats them? Giant tube worms, some reaching 6 feet in length, with bright red, hemoglobin-rich plumes waving in the chemically rich water. Mussels, clams, and specialized vent shrimp, often blind or with highly adapted eyes tuned only to the faint infrared glow of the hot water. It is a completely isolated, self-sustaining biological engine running on Earth's internal furnace. If you had to pick one place on Earth that felt truly alien, truly extraterrestrial, you'd pick a hydrothermal vent field. It's a hellscape that somehow became a cradle of life. Now, speaking of life in a hellscape, we have to talk about the undisputed champion of heat tolerance in the animal kingdom, the Pompeii worm, Alvinella pompejana. This creature lives right on the edge. It builds tubes directly onto the vent chimneys, positioning its tail end in water that can reach 80 degrees Celsius, 176 degrees Fahrenheit, hotter than any hot tub you've ever been in, while its head pokes out into the cooler water just a few inches away.
This means the Pompeii worm experiences the steepest temperature gradient of any known animal on Earth. Its body is literally half-boiled, half-chilled at any given moment. How does it survive this thermal torture? It's covered in a dense, hairy coat. But that coat isn't hair. It's a thick mat of symbiotic bacteria. These bacteria act as insulation, but more importantly, they are thought to detoxify the heavy metals and sulfur compounds that would otherwise kill the worm instantly. It's a perfect codependent relationship, forged in fire and toxic chemicals. The worm provides the bacteria a stable platform and nutrients, and the bacteria provide the worm with a protective shield. Seriously, think about that level of specialization. Life isn't just surviving down here, it's thriving by hacking the most extreme chemistry Earth can throw at it. If you are just tuning in and your mind is already blown by these deep-sea thermal hackers, please do me a favor, smash that like button. It helps this crazy descent reach more people who need to know about the unseen wonders beneath our feet. But the vents pose a massive biological mystery, one that scientists are still desperately trying to solve. How does vent life spread? These vent fields are incredibly ephemeral. They don't last forever. A typical black smoker might only be active for a few decades before the geological plumbing shifts, the chimney collapses, and the ecosystem dies out. So, if these communities are isolated oases separated by hundreds or even thousands of miles of cold, barren abyssal plain, how do the specialized organisms jump from one dying vent to a brand new erupting vent nearby? This is the vent hop theory. Scientists believe that vent organisms, particularly the larvae of worms and mussels, must enter a sort of suspended animation, drifting through the cold, dark waters until, by sheer luck, they encounter the faint chemical signature of a newly forming vent. It's a genetic lottery played out on a massive scale, relying on a combination of luck, ocean currents, and incredible biological resilience. The implications of this are huge. It means that the connectivity of life in the abyss is far more complex and reliant on chaotic geological events than we ever imagined. It's a life cycle dictated by catastrophe. All right, we've talked about the scorching heat of the vents. Now let's pivot to the absolute opposite extreme, the crushing, frozen isolation of the subglacial frontier. We are talking about environments that have been sealed off from the rest of the world for millions of years, trapped beneath monumental layers of ice. The crown jewel of this exploration is Lake Vostok in Antarctica.
Imagine looking at a map of Antarctica. It's a vast, white wasteland, right? But beneath the ice sheet, which is nearly 4 kilometers,
5 miles thick in some places, there are vast networks of liquid freshwater lakes. Lake Vostok is the largest of these. For roughly 15 million years, this lake has been sealed off.
No light, immense pressure from the overlying ice, and a temperature hovering right around freezing. But here is the kicker. The concentration of oxygen in the water is thought to be 50 times higher than typical freshwater lakes, because the ice compressing the water forces atmospheric gases into solution. For most surface life, that much oxygen would be toxic. It would literally rust their cells.
The challenge of sampling Vostok was immense. Scientists had to drill down almost 4 kilometers without contaminating the pristine, ancient water below. They used a combination of hot water drilling and special fluids that wouldn't freeze or introduce outside microbes.
It was a painstaking, decades-long process, driven by the ultimate question. After 15 million years of total isolation, what kind of life evolved down there? When they finally breached the lake, what they found was astonishing, though not immediately visible to the naked eye. They found an entire new biome of microbes.
Genetic sequencing revealed unique communities of bacteria and archaea. Some were extremophiles that seemed to thrive on the sheer pressure and the high oxygen levels. Others were adapted to chemosynthesis, likely feeding on the trace minerals released from the underlying bedrock, similar to the vents, but operating in slow motion under a massive frozen ceiling.
What this tells us is that life, given enough time and a stable energy source, even a tiny, slow one, will figure out a way to exist, no matter how harsh the conditions. Lake Vostok is literally a living time capsule, preserving a lineage of life that has been completely separated from the evolutionary pressures of the surface world for longer than most human species have existed. And here is where the deeper questions start to bubble up.
If specialized microbes can survive 15 million years in a sealed, pressurized, high-oxygen environment, what about larger organisms? The current samples mostly show single-celled life, but the lake is massive, about the size of Lake Ontario. Is it possible that there are multicellular organisms, perhaps transparent shrimp or slow-moving creatures that have adapted to the high-pressure, high-oxygen liquid environment?
We don't know yet, but the possibility is electrifying. It pushes the boundary of what we consider habitable. I want to hear your thoughts on this one. Do you think there are complex, multicellular creatures swimming around in Lake Vostok, sealed off from the sun for millions of years? Or is it purely a microbial world? Drop your theories in the comments below. And if you haven't yet, make sure you hit that notification bell.
We are about to zoom out and connect these extreme Earth environments to the ultimate unseen world, the search for alien life. You don't want to miss the next chapter of this descent, because, friends, the reason we care so much about the Pompeii worm, the Vostok bacteria, and the slow-motion zombie microbes is that they are our blueprints for exobiology.
They are the proof that life doesn't follow the rules we set for it. When we look up at the solar system, where do we see the most promising environments for life beyond Earth? We look at places that mirror our deep, unseen worlds.
Take Europa, Jupiter's massive moon. It's covered in a shell of ice, perhaps 15 to 25 kilometers thick. But beneath that ice, we are almost certain there is a vast saltwater ocean, kept liquid by the tidal forces of Jupiter flexing the moon's interior.
Sound familiar? It's Vostok on steroids. If life can survive under 4 kilometers of Antarctic ice, then the conditions on Europa, pressurized, dark, and potentially warmed by hydrothermal activity on its seafloor, are prime real estate for deep-sea life.
We might find European versions of tube worms, chemosynthetic bacteria, or even something far more bizarre. The energy source wouldn't be sunlight. It would be the heat and chemistry generated by the moon's rocky core interacting with the water. Then there is Enceladus, a tiny moon orbiting Saturn, which regularly blasts geysers of water vapor, ice particles, and organic molecules out into space.
This is a crucial finding because those geysers confirm a liquid subsurface ocean, and analysis of the plumes has detected hydrogen gas. Why is hydrogen gas a huge deal? On Earth, hydrogen is a key energy source for certain chemosynthetic microbes, particularly those found near hydrothermal vents. This suggests that Enceladus has a habitable zone where water is interacting with rock, creating the chemical energy gradients necessary to support life. It's a deep-sea hydrothermal vent system operating 790 million miles away from Earth. Our journey into the abyss, into the deep crust, and under the ice isn't just about cataloging strange creatures. It's about fundamentally redefining the parameters for life in the universe.
We used to think life needed the sun. We used to think liquid water was enough. Now we know life just needs an energy imbalance, a chemical gradient, and it will exploit it. Whether that gradient is powered by radioactive decay deep in the crust, superheated sulfur from a volcanic vent, or the immense pressure of an ice sheet. Every single extreme organism we've discussed, from the high-pressure snailfish to the high-temperature Pompeii worm, is a testament to life's incredible adaptability. They prove that the most common environment in the universe might not be the temperate surface, but the pressurized, dark, chemically charged subsurface. And that, my friends, is why the unseen worlds of Earth are the most important frontier in our search for cosmic neighbors. We are still only scratching the surface, literally and figuratively. We've mapped less than 20% of the ocean floor in high resolution, and the deep continental subsurface is still largely a mystery. There are countless Vostoks and countless black smokers waiting to be discovered, each potentially holding a new key to the origin and resilience of life. The descent continues, and the mysteries only deepen. We've covered fire and ice, pressure and darkness. But there is one final, terrifying frontier we haven't truly explored yet. A place that makes the Mariana Trench look like a kiddie pool. The realm of the deep biosphere and the limits of terrestrial heat. We know life exists meters below the surface, but how far down can we really go?
How deep can a microbe burrow before the heat from the Earth's core sterilizes everything? That is the next leg of our journey. And trust me, it's going to redefine what you think of as home. Before you click away, make sure you share this video with anyone who loves science, mystery, or just plain weird facts.
Help us spread the word about the incredible alien life thriving right here on Earth. We're building a community of deep-sea explorers, and your support keeps the lights on, even if those lights are just the faint bioluminescence of a deep-sea anglerfish. Thank you for joining me on this wild ride.
I'll see you in the comments, and I'll see you on the next descent.